So today we'll be looking at problem 3.4. This problem focuses on thermal resistances and conduction through a wall. To start out, I'll just read through the problem statement and highlight some of the important givens that we'll be using in the problem. So a dormitory at a large university built 50 years ago has exterior walls constructed of 30mm thick sheathing, like this, with a thermal conductivity shown here. To reduce heat losses in the winter, the university decides to encapsulate the entire dormitory by applying a layer of insulation. We have the thickness here. And we also have the thermal conductivity of the insulation here. To the exterior of the original sheathing, the extruded insulation is in turn covered with a thick layer of glass, with the thermal conductivity shown here. Determine the heat flux through the original and retrofitted walls when the interior and exterior air temperatures are shown here. The inner and outer convection heat transfer coefficients are given here. So now that we have the givens, and I have them kind of written out already on the left here, just to reiterate, we're looking for the heat flux from the original wall versus the heat flux through the retrofitted wall. And some of the equations that we'll be using a little bit later are shown on the right. Like I said, we're using the flux equation, and we'll be focusing on R double prime, the resistance of conduction and the resistance of convection. Just to visualize the problem a little bit better, I have the schematic shown below. The schematic on the left is the retrofitted version, and the schematic on the right is the original. Now that we kind of have this all fleshed out, we'll look at the assumptions and then actually get into the analysis of the problem. So in order to actually be able to solve this problem with thermal resistances, we will be looking at 1D conduction. So there will only be heat flow assumed in one direction. Also, we'll be using constant properties for the thermal conductivity and the heat transfer convective coefficients. And also, we'll be neglecting contact resistances between the different layers of the wall. As you can see down here, I already have the different resistors drawn out. The diagram on the left matches the retrofitted wall, and the diagram on the right matches the original wall. For the retrofitted wall, we have two convective resistors and three conductive resistors that align with the sheathing, the insulation, and the glass. And then on the right, we have two convective resistors and one conductive resistor, which is just for the sheathing. So going back to the equations we had before, R double prime conduction is just the length that the heat is traveling, so the thickness of the walls, and that is over the thermal conductivity of the wall. And then R double prime convection is just 1 over the heat transfer coefficient. So I have these written out already based on the givens that we have, but R double prime convection for the interior is given here as 0.2 Kelvin meter squared per watt. The R double prime convection on the outside is much smaller at 0.033. And then, as you can see, the largest conductive resistance is shown from the insulation at 1.03 Kelvin meter squared per watt. So now that we have all of these values, we can add them up as all of our resistors are in series in order to get the total resistance for each wall. And I have that shown here. So when we're looking at the total resistance of the original, we have the resistance of convection on the inside, the conduction from the sheathing, and the resistance of the convection on the outside. And you can see that the total resistance is just 0.533 Kelvin meter squared per watt. And for the retrofitted, we have convection of the inside, conduction of the sheathing, conduction of the insulation, conduction of the glass, and convection on the outside. And with that, we get 1.567, almost 3 times larger than our original. And because we're looking for the flux through both, we'll use the equation I showed above of the heat flux equals the change in temperature over the total resistance. And for the original, we have the change in temperature, which it was 22 degrees C on the inside, minus 0 degrees C on the outside, over our total, which gives us 41.25 watts per meter squared. And the retrofitted, we have 22 minus 0 like before, over the other total resistance, which was 1.567, and that gives us 14.04 watts per meter squared. These are our final answers for the problem. And just some comments on this. So like I said before, the largest resistance added is due to the insulation layer. I just wanted to point out that this resistance was 3.4 times larger than the original resistance due to the sheathing. And as you can see, it causes a major drop in total heat flux going through the wall, which will be good for the upgrade.